Okay, welcome back everyone. All right, so it looks like there's a fair bit of latency today. Hopefully that won't be too much of a problem. So we have a few minutes before class starts. As usual, I'll ask if anybody has any questions for me. Okay, so a few questions popped up. When will the assignment grade come out? That depends on which TA in particular was marking your assignment. So they all mark at different speeds and they all enter they basically enter their grades as they go. So depends who's grading your assignment. I've asked them, my TAs, I've asked them to have it done by the middle of this week, but everybody has sort of lots of things going on. So as soon as they're ready. Is there a way we can write the midterm at a different time rather than putting the whole grade into the final exam? Yes, it turns out that this trying to schedule two courses midterms at the same time, the two section midterms at the same time, is problematic for a lot of people. So I'll post a message soon about contacting me if you want to write at a separate time, and that there'll be one fixed separate time. I think it'll be in the evening. The last question too on assignment 1, could you use the sum rule instead of the product rule? I would have to remember what question 2 on assignment, last two questions on assignment 1 were. I don't remember those off the top of my head. Okay, so today we're continuing on recurrences. This is a really important topic in this course, and it's a really important topic in computer science. So recursive functions are something that come up all the time in computer science, and that what we do here in analyzing them helps us understand these things in lots of different ways, and we'll see an example of that today. But just remember, last class we'd introduced recurrences, and we saw these Fibonacci numbers defined by this recurrence. F of n is equal to n if n is 0 or 1. Otherwise, f of n is equal to f of n minus 1 plus f of n minus 2. That's the definition of the nth Fibonacci number as a recurrence. And we proved that actually it has a closed form that involves these irrational numbers, phi and psi. So you take phi to the n plus psi to the n, and you divide that by the square root of 5, and you actually get this integer, which is the nth Fibonacci number, remarkably. And the important thing to notice here was that phi was bigger than 1, and psi has an absolute value which is smaller than 1. So when you raise phi to the power n, it gets bigger and bigger and bigger. When you raise psi to the power n, it gets closer and closer to 0. And so a really good approximation for this thing is you just take phi to the n, divide by root 5, and that thing there is very close to the true value. In fact, it's within 1 of the true value of the nth Fibonacci number. So this is useful when we're trying to understand how quickly these Fibonacci numbers grow. And here's a list of the first 20 Fibonacci numbers. It doesn't look like they're growing too quickly. Already we get up to F19, which is only about 4,000. But this tells us it is growing exponentially. It's just the base is not quite base 2, right? Because 2 to the 19 is about 500,000. Here it only gets up to 4,000, but it is growing exponential. Okay, so now on to something completely different, or apparently so. So here's an innocuous question. How many ways can I write the integer n, so pick some positive integer n, as the sum of 2's and 1's? So for example, if n equals 1, then there's only one way to do that. So it's a sum of 1, 1. So that's what it looks like here. But if n equals 2, then there's actually 2 ways to do it, because I can write 1 plus 1, that's equal to 2, but also just 2 by itself is equal to 2. And if n is equal to 3, well, then we'll find by exhaustive search that there are 3 ways to do it. I can write 1 plus 1 plus 1, or I can write 1 plus 2, or I can write 2 plus 1. Okay? So what I'm counting here are basically the strings of 2's and 1's that add up to n. Right? So in this case, there's a string of length 1 and a string of length 2 that add up to 2. Here there's a string of length 3 that adds to 3. There's a string of length 2 that adds to 3, and there's another string of length 2 that adds to 3. Okay. All right, so that's what we want to count. And we'd like to know, for a general value of n, what's the number of these things. And we've sort of seen a strategy for modeling this kind of thing as a recurrence. So the general technique, and we've seen this for strings like binary strings that avoid 0, 0, and strings over the alphabet ABC that avoid AA, that you kind of look at the way it starts, so the beginning of this thing, the different ways to start it, and then hopefully the ways to finish it are already counted by some smaller recurrence. Okay? So we'll say, we'll define f of n is equal to the number of, exactly what I wrote up here, a number of ways to write n as the sum of 2s, and 1s. Okay? And we have seen that here we already know the first couple of these things. So f of 1, there it is. F of 2, there it is. There's two ways to do it. We can even go back a step and say, what's f of 0? Well, how many ways are there to write 0 by a sum of a string of zeros, of 1s and 2s? Well, there actually is a way to do that, and that is like this. So f of 0 is 1, because I can sort of interpret that as nothing on the left-hand side. So an empty sum on the left-hand side is equal to 0. All right. And now we want a general formula. So we have it for from small values of n. So let's say that n is bigger than 2 or bigger than or equal to 2. It doesn't really matter. Let's figure it out. So for n, let's say bigger than or equal to 2, we can do the following. So we want to write this sum of 1s and 2s that add up to n. We can either start with a 1, or we can start with a 2. Okay. So if I start with a 1, then it's going to be 1 plus something. And what is that something here? Right? I'm going to have an equation that looks like 1 plus something, and it's supposed to add up to n. Well, what is this something? Well, this is a string of 1s and 2s that adds up to n minus 1. Okay. So here, this can be any string of 1s and 2s, or any sum of 1s and 2s, that adds to n minus 1. How many such things are there? Well, we have a name for that. The definition, by definition, the number of such strings is f of n minus 1. Okay? So, followed by any sum of 1s and 2s that adds up to n, and that means there's f of n minus 1 possible ways to complete this thing. Or our string starts with a 2, we add something else to it, and then together that all adds up to n. Well, this is anything that adds up to n minus 2. Well, the number of things that add up to n minus 2, we have a name for. It's f of n minus 2. Any So the number of these things, number of strings of 1s and 2s that add up to n minus 2, that's f of n minus 2. Okay. And so we're trying to determine the size of some set, S, which is the set of all strings of 1s and 2s that add up to n. And we split it into two parts, A, which is those strings that start with a 1, and B, which is those strings that start with a 2. Those two parts are disjoint, right? A string either starts with a 1 or it starts with a 2. It can't start with both of those things. So that means the size of our set is the sum of the sizes of these two sets. That's the sum rule, right? The set we're trying to count is a disjoint union of A and B. So the sum rule applies to it. So that just translates into f of n is equal to f of n minus 1, that's this part, plus f of n minus 2. Well, that's a familiar looking sum. That looks like the general form of the Fibonacci recurrence, right? F of n equals f of n minus 1 plus f of n minus 2. It is not exactly the Fibonacci recurrence, though, because things don't quite line up. So f of 1 equals 1, f of 2 equals 2, but in the Fibonacci recurrence you don't get to 2 until f of 3. So they're off by 1, but still that just means that f of n in general is equal to little f, the Fibonacci number, n plus 1. Okay. So the number of ways to write n as a sum of 1s and 2s is the n plus 1th Fibonacci number. All right. So, and these Fibonacci numbers and their generalizations tend to pop up in a lot of problems like this. So much so that there's even a journal devoted to Fibonacci numbers. It's called Fibonacci Quarterly, where people write theorems about Fibonacci numbers and things that are counted by Fibonacci numbers and various generalizations of Fibonacci numbers. So it's a rich field of study. How do you count the number of ways to make n dollars with coins? Well, that depends on the number of, it depends on the number and denomination of coins that you have, right? But you can imagine if you want to make n dollars with, let's say, loonies and quarters, then you're going to get some recurrence that looks something like, better to use cents, but the way to make some number of cents with only quarters and loonies is going to be something like, well, such a thing starts with, well, okay, we should be careful. If you're asking the question, how many ways are there to make n dollars with quarters and loonies, and then write down those, take those quarters and loonies and put them in a line in a specific order. How many ways are there to do that? Then you get a recurrence that looks something like f of n is equal to f of n minus 25 plus f of n minus 100. So either the first thing is 25 cents or the first thing is 100 cents, a loonie. So you get a recurrence that looks like that, if that's what you're trying to count. If you don't care about the order of the quarters and the loonies, then that's a different story. Okay. What does the lowercase fn plus 1 represent? It's exactly this Fibonacci number over here. So that's this one. Okay. All right, so there's another example where Fibonacci numbers pop up. Now, thus far in this course, well, this is a computer science course, and I've been somehow claiming that all of this stuff is relevant to computer science, but I haven't really been backing that up. So we haven't done any really compelling examples which show that somehow the size of the sets that we're counting has something to do with computers. So next we will look at an example where the connection with computing is extremely clear. And this is just the beginning of where this starts. This is just one sort of nice example, but basically, right, a common thing in computing is recursive functions, recursion, and these recurrence equations that we do here. They often capture the running time of recursive functions, and that's what happens here. And in this case, it happens in an extremely non-obvious way. All right, so we have to go back about 3,500 years. No, not so much, only 2,300 years to an algorithm that was designed for a problem that people studied even 2,300 years ago. So this is for the greatest common divisor. And the algorithm that we're going to study is Euclid's algorithm. You may have heard of this guy before, sort of famous for geometry. Euclidean geometry is named after Euclid. But Euclid also did computation, and in fact was interested, with geometry, was interested in computation and the efficiency of geometric constructions. But sometimes there were just numerical problems to solve, and Euclid's algorithm solves one of those things. So it finds the GCD, that's this thing here, of two integers, A, which is bigger than B, which is bigger than or equal to 1. Okay. So this is the largest integer that divides both A and B. So the largest integer D that divides A and also divides B. Okay. So for example, the greatest common divisor of 20 and 15. So what's the biggest integer that divides both of them? Well, it's not 15 because 20 divided by 15 is not an integer. And it's not 10 because 15 divided by 10 is 1.5. That's not an integer. It's actually 5. So the biggest integer that divides 20 and also divides 15 is 5, because 20 divided by 5 is 4, 15 divided by 5 is 3. This is an integer, and this is an integer, and we can try all of the other integers, the bigger ones, to see if there's anything bigger than 5 that works, and nothing does. I think it's clear we don't have to try anything bigger than 15, because certainly if we take anything bigger than 15, then 15 divided by that thing is smaller than 1, but still bigger than 0, so it's not an integer. So we could try the other things, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and realize this is the largest one that works. Okay? So that's what we want to do. And it uses the mod operator. So this mod operator is the remainder after integer division. So let me try and explain this semi-formally by saying the following. For any integers, actually let me make life a bit easier so we don't have to think too hard. Let's say positive integers. A and B, we can always write A is equal to Q times B plus R, where Q is an integer and R is also an integer, but from a very specific set. It's in the set 0 up to B minus 1. Okay? So R is an integer that's smaller than B, actually strictly smaller than B, and bigger than or equal to 0. Right? So, for example, if I take A equals 20 and B equals 6, then A is equal to 3 times B plus 2. Okay? 3 here is the value Q, and B here is the value R. And so this kind of gives two things. There's integer division, which is when we're asking about the value Q. So A divided by B, if I use integer division, I'll get this value Q, and A mod B is this remainder, R. Okay? So, so A mod B is equal to this remainder R. So it's this unique integer R that I get when I write A in this form. Okay. And so of course A mod B then is from this set 0 through B minus 1. All right. So let's take a look at a couple more examples. 17 mod 12, for example. That I can write as 17 is equal to 1 times 12 plus 5. So there's the mod. So that's equal to 5. Another example, here's 123 mod 1. So mod 1 is important. It actually shows up in the algorithm. So what does that mean? Well, I have to write 23 in this form. So 23 is equal to 23 times 1 plus 0, right? So in this case, this is my value Q, this is my value R, so 23 mod 1 is actually equal to 0. And I think you see there's nothing special about 23 here. If I put any integer here and ask for it mod 1, then I'm going to get 0. And 45 mod 15. How did we get that? Well, 45 is equal to 3 times 15 plus 0. 3 times 15 is already 45, so there's no remainder here. Okay. So that's also 0. And this is a useful example because, well, if I see that A mod B is equal to 0, that means that B divides A. So B is a divisor of A, and well, B is a divisor of itself because B divided by B is 1. So that looks like it means that the GCD of A and B in that case is actually just B, if B is the smaller of the two numbers. So let's just write that down. So Euclid's algorithm is supposed to find the greatest common divisor of A and B, where A is bigger than B is bigger than or equal to 1. And it uses the mod operation, so we'll write down this useful piece of information, which is if A mod B is equal to 0, then the GCD of A and B is equal to B. Right, because A mod B is equal to 0 means that A is equal to Q times B plus 0. And so that means that A divided by B is equal to Q. So that's an integer. So B does indeed divide A, so B is a divisor of A. And of course, B divided by B is equal to 1. That's also an integer, so B divides itself. And so, so that the GCD then of A and B is just B. Okay. All right, so because of the latency, anytime you have a question, just write it down quickly. I'll keep coming back and checking the iPad to see if questions have come up. But there's where we're at right now. All right, so, and here's the basis of Euclid's algorithm, which is if the GCD of A and B is equal to R, which is not equal to 0, because we know what to do if sorry, not GCD, A mod B. If A mod B is equal to R, which is not equal to 0, because if A mod B equals 0, we know the answer. The answer is just B. But suppose it's equal to R, which is not equal to 0, then something interesting happens. The GCD of A and B is actually equal to the GCD of B and R. Okay. So here's a good test, and in fact Euclid's algorithm, we'll write it down in a minute, but it's basically this. Compute A mod B. If it's equal to 0, you're done. If not, then you recurse on B and that remainder, that A mod B. Okay? That's Euclid's algorithm. And this lemma is what's going to argue that that is correct. And the proof is just the following. So you let D be any common divisor of A and B. So claim is that the greatest common divisor of B and R is the same as the greatest common divisor of A and B. So let's just take any divisor. Could be the greatest one, could be any one. So what does that mean? That means A divided by D is an integer, and it means B divided by D is an integer. So both of these things are integers. Now, A, by definition, is equal to Q times B plus R. And this is where R is equal to A mod B. That's the definition of mod, and R here is in the range 0 through B minus 1. So A is equal to this. Now A divided by D, so we can divide this whole equation both sides by D. So we get A divided by D, we get A divided by D, we get R divided by D. So what do we have here? A divided by D, well, D is a common divisor of A and B, so this is an integer. Over here, we have B divided by D, which, because D is a common divisor of A and B, it's a divisor of B, so this is an integer. And Q, by the definition of mod, this is also an integer. So on the left-hand side, we have an integer is equal to an integer plus something. Now, that something is R over D, and the only way that that can be true, that you get an integer is equal to an integer plus something, is if this thing is also an integer. So what this means is that every common divisor of A and B is also a divisor of R. And that holds also for every divisor, so it holds for the greatest common divisor. Okay. So what you get then is that every divisor, including the greatest common divisor, is also a divisor of R. So the greatest common divisor that you get here is on the right-hand side is the same as the one on the left-hand side. In fact, and it also works the other way. Every common divisor of B and R is a common divisor of A and B. Okay. So this is the basis of the thing. This is the thing that says Euclid's algorithm is correct. So let me just write down Euclid's algorithm. Euclid, A, B. So this requires A is bigger than B is bigger than or equal to 1, And it just computes R is equal to A mod B. If R is equal to 0, then return B. Otherwise, we didn't return, we return the GCD of B and R. This line gives the correct answer because of this, and this line gives the correct answer because of this lemma. Okay. And why doesn't this algorithm run forever? Well, it doesn't run forever because R is in 0 up to B minus 1. Right? The remainder, when I divide by B, is a number that is smaller than B. And in particular, R is less than B, which means that it's also less than A. So the arguments to GCD get smaller, right? So when I make this recursive call, instead of having the first argument I have something smaller. It's now B, which was smaller by definition. And instead of having the second argument being B, I have R here, which is smaller than B. So both of the arguments get smaller, and none of them are ever equal to 0. So at some point, the smaller of the two arguments has to be equal to 1. So eventually, if this could go on for a long time, and it could go all the way down until I recurse, and that second argument is equal to 1. And just for so I should be calling this thing recursive. So it's a function with the same name, Euclid BR, which is computing the GCD. Okay. So take a look at a quick example or two. So let's try the GCD of 75 and 45. Or Euclid 75, 45. So what happens there? Well, 75 is equal to 1 times 45 plus 30. Okay. So that means that 75 mod 45 is equal to 30, which then means that the GCD of 75 and 45 is equal to the GCD of 45 and 30. Now, 45 is equal to 1 times 30 plus 15. So 45 mod 30 is equal to 15, which means that the GCD of 45 and 30 is equal to the GCD of 30 and 15. So Euclid's algorithm, given 75, 45, calls itself recursively with 45, 30, which calls itself recursively with 30, 15. And now finally, 30 is equal to 2 times 15 plus 0, which means that 30 mod 15 is equal to 0. And so the algorithm returns B, which is 15. Okay. So that's the way Euclid's algorithm works. Computes the remainder. If the remainder is 0, it knows the answer is B. Otherwise, it calls itself with B and the remainder. All right. So there's one example. Let's do one more. So this lemma, we don't need to keep it written here because it had just better be true because of the way the algorithm is written, I think, reminds us what the lemma says. So if I do, let's say, GCD of 34 and let's pick a random number, 21. All right, so here we get 34 is equal to 1 times 21 plus 13. So the remainder is 13. So that tells us that the GCD of 34 and 21 is the GCD of 21 and 13. Okay, so 21 is equal to 1 times 13 plus 8, which tells us that the GCD of 21 and 13 is equal to the GCD of 13 and 8. And if I do that again, 13 is equal to 8 plus 5. So this is 8 and 5. And if I do this again, 8 is equal to 5 plus 3. So I get that. 5 is equal to 3 plus 2. So I get that. 3 is equal to 2 plus 1. And 2 mod 1 is 0. So the answer that I get in the end is 1. Okay. So there's another sort of long example. The numbers were smaller, but it actually took more steps. This was 7545. It was done with, here's 1 step, 2 steps, and then call that the third step. So it would be the number of steps is the number of equalities that I have here, 3 in this case. And here there's 1, 2, 3, 4, 5, 6, 7 steps. Okay, so someone asks, is this quick? Yes. So what we're going to argue is that this Euclid's GCD algorithm is actually very efficient. Okay. I don't understand when GCD divides R, why GCD of A and B is equal to GCD of B and R. So, so all of the divisors of A and B, the common divisors of A and B, are also common divisors of B and R. In particular, then, the greatest common divisor of A and B is the greatest common divisor of B and R. So the greatest common divisor of B and R can't be bigger than the greatest common divisor of A and B, because the greatest common divisor of B and R is smaller than B. Let's leave it at that. Okay, so is the algorithm quick? That's the question. And the answer is yes. We'll see why. And while I warm up for that, take a look at the 2 examples that I've just done and notice if you see anything. In fact, I'll erase one of the examples and take a look at the other one and notice if you see anything. Okay. Yeah, so I think you've seen it. Someone noticed even while I was doing the example that somehow the Fibonacci sequence is showing up here. For instance, if we look at the value of A, it goes 34, 21, 13, 8, 5, 3, 2, 1, which is 34, 21, 13, 8, 5, 3, 2, 1. So somehow this looks like it has something to do with this Fibonacci sequence. And indeed, you'll find that if you take two consecutive Fibonacci numbers and you give them to this algorithm, so here the two numbers were 34 and 21, so the smaller one is the second argument, the value of B, the larger one is the first argument, the value of A, then the number of steps, or not the number of steps, but the sequence of numbers you see that A takes on will be the Fibonacci sequence leading down to 2, and actually B will take on the Fibonacci sequence leading down to 1. Looks cool, but that just happens to be when you pick numbers that are Fibonacci numbers. Maybe there are bad numbers. So let's define, because we want to study this algorithm and we want to talk about running times, but I don't want to deal with the cost of arithmetic. In particular, this GCD algorithm, it's so fast that people use it for really big integers. So for instance, in public key cryptography, this GCD algorithm gets used, but the integers aren't like 32-bit integers or 64-bit integers. They're like 2,000-bit integers, or sometimes even 10,000-bit integers, which means that even something as simple as this mod operation, which in a programming language where you have small integers, it's usually just represented using the percent symbol. That's not a constant time operation if the integers are that big. Okay? And I don't want to talk about how you do arithmetic with large integers. So instead, I'm just going to count how many mod operations this algorithm does. That's the concrete thing that I can count. How many mod operations this algorithm does. When I give it the arguments A and B, how many pairs of integers does it end up having to compute the mod of? And here we see that there is 1, 2, 3, 4, 5, 6, 7. So each of these things involves one mod operation. So M of 34 21 is equal to 7. And although it's gone, I think we saw that m of 75, and what was that example? 45. That was done in 3 steps. So now we have something concrete to count. We'll say that's the running time of the algorithm. How many mod operations does it do? It's a good stand-in because there's nothing else really that the algorithm does other than this mod operation, right? Every time it's called, it does a mod operation, then it checks if the result is 0. That's not very exciting. And then if it's called again, the first thing it does is a mod operation. Okay? So counting mod operations is basically the same as counting the number of recursive calls. All right, so here's the claim. Let A bigger than B bigger than or equal to 1, and let little m is equal to m A B, then A is bigger than or equal to, let me not get the index wrong, the Fibonacci number m plus 2, and B is bigger than or equal to the Fibonacci number m plus 1. So, Fibonacci number. And the same thing with this one. It's a Fibonacci number. Okay. So, this, again, looks crazy. Because there's nothing in Euclid's algorithm here that looks at all like a Fibonacci sequence. Right? The recurrence has a, I mean, you take the remainder, you call B on the remainder. This doesn't look anything like f of n equals f of n minus 1 plus f of n minus 2. And yet somehow these Fibonacci things show up. That we're going to be able to prove this. And actually, turns out this is tight. So you can't prove anything stronger than this, because when you take 2 consecutive Fibonacci numbers and use them as input, you actually get exactly that many mod operations happening. Okay. So here we had 7 mod operations. That's how many mod operations were performed in computing the GCD of 34 and 21. So this says, well, that must mean that A is bigger than or equal to f of 7 plus 2, so f of 9. Yep, that's 34. And this tells you that B must be bigger than or equal to f of 7 plus 1, f of 8. That's 21, and indeed. So it matches perfectly. All right. So how in the world does one prove something like this? Well, it's a recurrence, so it seems natural that we're going to do induction on something. And we have somehow this number m, which is counting the number of steps, number of recursive steps, basically. So m is a natural candidate to use for the induction variable. So the proof is by induction on M. And let's try some base cases. So here's one. Let's try the base case M equals 1. So is that the base case? Yeah. If I call Euclid's algorithm with arguments, valid arguments, then the first thing it does is do a mod operation. So there's no way to call it without it doing at least one mod operation. Okay? So there's no, it doesn't make sense to consider this for m equals 0. So m equals 1 is the first meaningful thing. All right, but then there's not too much to do. So if m equals 1, well, all we know is that we required that a was bigger than b and b was bigger than or equal to 1. So, so we get a is bigger than b, which is bigger than or equal to 1. Well, so if a is bigger than b, that means a, and b is bigger than or equal to 1, that means a is bigger than or equal to 2. So let's take a look. This says that b should be bigger than f of 1 plus 1. Right, that's what this says. For m, if the number is m, b should be bigger than f of m plus 1. So this should be bigger than or equal to f of 1 plus 1. This is f of 2. Let's look over. F of 2 is 1. There it is. So that checks out. So that part of it checks out. And a, according to this, should be bigger than or equal to f of 1 plus 2, which is f of 3, which is equal to 2. And that checks out. Basically, because we don't accept arguments. We don't accept an argument b, which is less than 1, and we don't accept an argument a, which is not bigger than b, which means it's bigger than or equal to 2. So that base case checks out. Good. And so now, suppose, well, let's be long-winded about it. Assume that this is true for all k in 1 up to m minus 1. And now prove for m. So if m is bigger than 1, so m bigger than or equal to 2. So if m is bigger than or equal to 2, that means the algorithm doesn't stop immediately. It makes at least one recursive call. Okay? So that means that the GCD of A and B is equal to the GCD of B and R, the remainder. Okay? Because the remainder wasn't 0, otherwise m would be equal to 1. So the remainder of, so A mod B is not equal to 0, otherwise m equals 1, which means that this is true. A mod B is not 0, so this is true. That's what that theorem was. Now, what is m of A and B? Well, for m of A and B, the algorithm does one mod operation, and then it calls itself recursively on B and R. Okay. So we end up with this kind of recurrence for M. But we're assuming that the GCD of A and B, the number of mod operations performed when we compute the GCD of A and B is M. So this thing here, by definition, is equal to M. So M is equal to 1 plus little m is equal to 1 plus m of BR, which means that m of BR is equal to little m minus 1. So another way of saying that is that if I use Euclid's algorithm to compute the GCD of these two numbers, then this is how many mod operations are performed. Now, the inductive hypothesis tells us something about B and R now, because we know that if we compute their GCDs, that this many mod operations were performed. In fact, the inductive hypothesis tells us, what does it tell us about B? B is the first argument here. So it tells us that B is bigger than or equal to F. Now, it takes m minus 1 steps, so we get a m minus 1 plus 2. The first argument gets a plus 2. So this is f of m plus 1. And it also tells us about R. What does it tell us about R? It tells us that R is bigger than or equal to, well, we take f of m minus 1. That's what we have here. And then we add 1. Okay. So, so here we know something now. We know B is bigger than or equal to f of m plus 1. That means we're half done. We needed to prove that B was bigger than or equal to f of m plus 1, and here we get it. Why did we get it? We get it because when we make the recursive call, B is the first argument. There's going to be one less mod operation to do, but we already know that if it takes this many mod operations, then we have to, the value of the first argument is bigger than f of m plus 1. So we've proved part of it. We proved the bound on B, but now we still haven't shown that A is bigger than f of m plus 2. But what is A? A, well, we know A because of the definition of mod. A is equal to Q times B plus R. So when we take A and divide by B, we get Q plus a remainder. Now, A we know A is bigger than B. That's a requirement of the input. That means that A divided by B is bigger than 1. So that means that the Q here, so if A divided by B is bigger than 1, that means that I get at least 1 for Q plus a remainder. Maybe I get 2, 3, any number for Q, but I don't get 0 for Q because A is bigger than B. So this means that Q is bigger than or equal to 1. So that means that this thing, let's just replace Q with something that's not smaller, that's not bigger rather. So that means this thing is bigger than or equal to B plus R. But wait a minute. So A is bigger than or equal to B plus R, but B we know is bigger than or equal to f of m plus 1. And R is bigger than or equal to f of m. But wait a minute, this is a Fibonacci number, m plus 1. This is a Fibonacci number, m. That means that this, their sum, is the m plus 2th Fibonacci number. So A is bigger than or equal to f of m plus 2, which is exactly what we needed to prove. Okay. So we got the bound on B already here, and then for the bound on A, we use the definition of mod, and the fact that when you take A divided by B and only keep the integer part, you get something that's at least 1 if A is bigger than B. So that's the second part. So, like magic, somehow this Euclid's GCD algorithm gets bounded by, basically you say if the algorithm takes a long time, m steps, that means its inputs are big. The first one is bigger than the m plus 2th Fibonacci number, and the second one is bigger than the m plus 1th Fibonacci number. Intuitively, this means that unless we give this thing really big numbers, bigger than these Fibonacci numbers, it's not going to take very many steps. And we'll write that out the inverse way. We'll write that out in a second, but that's the idea, is that to make it run a long time, you have to give it really big numbers. Both A and B have to be really big numbers. So this is an extremely cool connection between Fibonacci numbers and something that did not look at all like it would have anything to do with Fibonacci numbers. So now let's look at what we said about these Fibonacci numbers. So to write this in a way that somehow makes more sense, like usually when we talk about the running time of an algorithm, we say, well, if I give it an input of size n, then it takes this much time, log n time or n log n time or something. This is a sort of inverted way of saying it that says, well, if it takes this much time, then the input was at least this big. So let's try and write it in the natural way. And so for that, we should understand this thing. There's this nice approximation here that I said, basically, the nth Fibonacci number is roughly rho to the n divided by square root 5. Okay? So So if it runs for n steps, m steps, a is bigger than or equal to f of m plus 2. That means that, well, we can use this thing. A must be bigger than or equal to rho to the n divided by square root of 5 plus 1. Yeah. That means a minus 1 is bigger than or equal to rho to the n divided by square root of 5, which means that a minus 1 times the square root of 5 is bigger than or equal to rho to the n. And now let's take the logarithm of both sides. So if I take the logarithm on this side, I get that log of square root 5 a minus 1 is bigger than or equal to n log phi. Right, if I take the logarithm of something raised to an exponent like this, it's the log of the base times the exponent, which, let's write it, oh, sorry, not n, these should all be m's. Okay, and let's write this now nice way. So here we get log of a minus 1. This is plus a log of a square root 5. We're going to divide everything by log of rho. So this thing here is the number of mod operations performed by the algorithm. It's at most the log base rho of a minus 1. Okay. Yeah, actually, no. There's a couple of plus 2's that I forgot. Okay, so it's a little, there's a little bit of a mess. M plus 2 comes over here. That one doesn't need to be divided. Yeah. There we go. So the number of mod operations done by this thing is basically the log of a minus 1 divided by the log of rho. So that here, if you evaluate this and look at what this means, this is about, oh darn, looks like something like 1.6, I'm going to say 1.618. It's not, this is not exactly correct. Log based 2 of a. And all of this stuff, well, root 5 is a constant, this is a constant, there's a minus 2 here, who knows if this is positive or negative, doesn't matter, it's a constant. So the running time of this, this algorithm, or the number of mod operations, is only proportional to the logarithm of a. So that means I need to put an enormous number in here to make this thing big. So it runs in basically order log a time. Rho to the n, no, not rho. I should have been saying phi. I was saying rho, but we've never defined a rho. Phi. Okay. So there, I think, is probably the first real example in this course where some really fine, precise, in this case, solving of a recurrence relation has a direct, like a straight, direct application to something that we really care about, the running time of an algorithm. In fact, it's super precise. And this is a very precise looking statement. And what's nice about it is we can't say anything stronger than this because, well, we know of examples. When you take these two consecutive Fibonacci numbers, this is exactly the number of mod operations that happen. For other numbers, kind of random looking ones, it's usually faster than this, but in the very, very worst case, this is exactly what happens. Okay, so that's a good place to stop there. The moral is that the Euclid's algorithm finishes in a logarithmic number of steps. The base of the logarithm is this, the golden ratio. Okay, so we have a couple of minutes. I can answer questions. What does it say before? This is just a 1. So this is a number that is bigger than 1 but smaller than 2. It's actually whatever log base 2 of 1 plus the square root of 5 divided by 2. This thing here is exactly that. Okay, so it's quiet in the chat. I will take that to mean that there are no more questions. All right, thanks for showing up again. It's always nice to have some live audience. So see you on Wednesday.